We now are into chapter 23, which deals with phase diagrams, and we start off discussing things in a real qualitative way. You may or may not have seen phase diagrams at some other point in your chemistry progression. So this might be a little bit of review, but just take it seriously, take good notes. I'm going to talk about a lot of important things. Make sure as much as you need, you pause the video, write down definitions, write down questions you might have as we go through things. We saw phase diagrams earlier in the semester, so just a quick little recap. Those phase diagrams were different. Those phase diagrams were PV phase diagrams, and you remember they had this kind of form where we had a coexistence region here. We could draw isotherms through them, we could find dew and bubble points, etc. What's different about this phase diagram is when we're now looking at P and T dependence on the state of a chemical system instead of P and V. So remember those three-dimensional diagrams we had? This is like rotating it and now looking at pressure and temperature. This coexistence region, I know it's kind of hard to see, but imagine rotating that three-dimensional structure. This coexistence region here becomes a line when you look at it from this angle. All right, so what's different about these diagrams is that it's pressure and temperature dependence, and we're going to try to find state and phase change information inside here. Now, why this is more useful when we're discussing phase changes is because these are easier experimental controls for us to actually enact on a chemical system. And if you think about actually making a phase change, what do you like naturally say you do? Oh, well, I'm going to heat it, okay? So temperature's an easy control. We control the pressure of situations, or we could leave it open to the atmosphere. Okay, so let's go through and if you haven't done so already, pause the video and draw this structure. And what we're going to be doing is filling in information inside here and then about it. And like I said, don't just kind of write down what we write here, also write down what's said, write really good notes. So this is the general structure that you'll see. We'll talk about some deviations for systems like water in terms of what this general structure looks like, right? But essentially what we have here are three distinct lines, right? And each one of these lines that I've colored a different color are coexistence regions. So these are situations where our one species that we're looking at, our one chemical species, in a closed system, right? So not open to the atmosphere or anything like that. At equilibrium, these guys are where you'll see more than one phase exist, okay? So let's try to fill in the blanks here in terms of what phases exist in these spots, so then we'll understand what these coexistence regions are. So just through our understanding of how things behave and temperature as being a measure of kinetic energy and motion, and pressure being a measure of how much we're forcing things together or how much the actual system feels compressed, all right? Here we have low temperature situations and high compression. Over here, it makes sense that we have our solid phase, okay? And like I said, temperature is usually the thing you can kind of think of as in easier terms. When we get to low temperatures, what do things do? They turn into solids because there's not enough motion to break the intermolecular forces to make anything but these like crystalline type structures, okay? And we see that solid phase exists for high pressures and low pressures, right? We also know that as pressure goes low and also as temperature goes high, if we're not forcing things together, right, because we have low pressures and they're not interacting a lot, and we have high motion in the system, right, no interactions, high motion, down here it makes sense that this is where we have our vapor or our gas phases, right? If we take a gas and it has a certain amount of motion, but we start to force things together, we start to make the system pressurized and those interactions start to come into play, what we eventually get is condensation into a liquid, right? But there's still too much motion, right, to completely solidify. So then we're left with just that liquid state. It's a condensed state, but it definitely has more motion than a solid. So it should be pretty straightforward, and make sure you can make the arguments yourself as to which one of these regions gets which label in terms of the state, all right? So that means this curve right here, right? This is where we're going to have a solid and liquid, right, for this one species that we're looking at in a closed system at equilibrium, right? This is where we're going to have a solid and liquid coexist with each other. So this is the solid-liquid coexistence region, right? Now, what we might call this is our melting point curve, and we'll talk about that in a bit, right? But think of it now as where solid and liquid can coexist. This curve right here, then this blue curve, this is where our liquid and gas will coexist, right? So this gets a couple different names. This is called the boiling point curve, but that implies like it has to be boiling and it doesn't. So I like to call it the vapor pressure curve. That's our coexistence region in our other diagram, our PV diagram, and it turned into this line here, all right? But that's where liquid and gas, they exist together, okay? This down here, then, this red curve, is where solid and gas coexist, all right? Now this we're gonna label as our sublimation curve. All right, sublimation curve. I'm gonna spell sublimation, oh, sorry about that. I'm gonna spell sublimation down here more clearly. Okay, so that's where solid and gas can coexist together. The only other region I want to label down here is this region right here. We're gonna call this the supercritical region. And we'll get to that in a second. But now we have everything labeled in terms of regions on our diagram, all right? While we introduced it, let's talk about sublimation, all right? So what happens on this curve is solid and gas can coexist together. So sublimation, you may or may not have heard about, all right? This is a process where a solid, right, turns directly into a liquid. So if I'm talking about going in this region, all right, going from a certain pressure or at a certain pressure, going from a lower temperature to a higher temperature and going in that direction, we would call that sublimation, right? The opposite of sublimation, right? What if I have a higher temperature, like gaseous situation, and I'm down here in terms of these pressures of my system, and now I move in this direction for the actual physical process. I cool down the system. That process is called deposition. Right, deposition. And deposition is the opposite of sublimation. So deposition is the physical process where a gas becomes a solid, and it does so directly without going through a liquid state. Actually, experimentally, sublimation and deposition, they're actually hard to observe because experimentally it's really hard to get a closed system, and that's one thing I'm going to stress again and again. For this, it's just that one species, like say we were looking at water, everything about this phase diagram then is just water. Well, as soon as you open water up to the atmosphere, then you don't have pure water. So we're going to be able to pull information from the phase diagrams about a species, but when you think about what this actual phase diagram indicates, it indicates the behavior of just that species alone, closed off from everything else. So sublimation and deposition, sublimation and deposition is actually hard to observe experimentally, right? So what are the other important parts to see on this curve? The other important parts to know in this curve are these two black dots that I have, right? Right here, right? That dot right there, I'm gonna label it TP because that is the triple point, all right? So sometimes on phase diagrams, you see triple points. Some phase diagrams have multiple triple points. You never have a quadruple point or anything like that. Triple points are regions on a phase diagram where 3 phases exist in equilibrium. So the regions on a phase diagram, they're really points. So they're points on a phase diagram, maybe it's better, sorry. Points on a phase diagram where 3 phases exist in equilibrium. So the standard one is between a solid, liquid, and gas, but you could have multiple solid phases, and whenever you see like 3 regions just coexisting, there's a point that's going to be there, all right, that we're going to label as the triple point. right? The thing about the triple point that's important for us from an experimental standpoint is the triple point kind of tells us something about when you can actually start to get liquids. The way that we like to think about things is working up in pressure, right? So if we're dealing with pressures that are up here, okay, yep, then solids, liquids, and gases are possible. But if we're dealing with pressures down here, notice that liquids are not possible at all. So the triple point is kind of interesting because it gives us an idea whether we'll see liquid behavior or not. Okay. The other point to label on this diagram, right, is up here. And this is a point we're familiar with, and that is the critical point. So I'm going to label it CP. That gets the same definition as earlier in the semester, all right? The critical point defines the temperature and the pressure, right? Where above that, you can't get a gas to condense to a liquid, okay? So I'm just going to clean this up a bit and redraw this. So here's my P, here's my T, triple point, up, critical point, right? So it kind of makes sense if you think about our definition from earlier semester, right? Here, down here, this would be the critical temperature. So let's label that T sub C like we were doing earlier in the semester. Notice what you have then for all higher temperatures. Higher temperatures are this way in the axis, right? The labels that we'll have is down here we have gases, just like there were gases here, right? And then up here, right, we're going to label this as a gas, but notice it was called the supercritical region, right? Now we're going to talk about that a bit. It's technically both a gas and a liquid, but via our definition of critical point, we can kind of think about it as a gas that has liquid-like properties, right? So up in this region, right, which means if you kind of look at it, here's your P sub C. So we have a certain critical temperature, we have a certain critical pressure. So we have this gas that exists at the critical point, and now we're forcing interactions. We're going up on this axis, and we're taking all those gas particles now, and we're trying to force them together, and we're making them interact. That supercritical region then has some odd things occurring because that supercritical region is going to contain what we call supercritical fluids. And these are really interesting chemical systems, but we don't need to know a lot about them for physical chemistry, so we're just a couple different ideas, right? So it's like a gas that has certain properties that resemble liquid properties. So up in that supercritical region where you're above TC and you're above PC, right? Remember, so it's T greater than TC and P greater than PC. That's defining where you'll find these, right? You have gases that are behaving in certain ways like liquids. And that's all you really have to know, all right? Just kind of think about it as it's being condensed so much that it starts to pick up liquid-like properties, but it's definitely still a gas, all right? And we can talk about effusion, diffusion, viscosity if we wanted to get into more detail, but I don't really want to. So this is all you need to know. So just know that experimentally some interesting things happen because you're condensing a gas, but it stays a gas, but it's picking up liquid properties, all right, supercritical fluids. The other thing I have to say about the supercritical region, and just following these curves in general, right, is we can use our curve in a lot of different ways. There's going to be a lot of different important information on it, a lot of bits of information that are important, right? All right. So one thing we can do is we can start to ask ourselves, all right, even though this is just one like chemical system and we're eventually going to open it up and some of the properties will change about how that system behaves, we can still pull off some important information about our chemical system. So for example, when we have these diagrams, we can ask ourselves about normal boiling points. And so we have to remember our definitions. Remember that normal means 1 atmosphere. Also, I'll remind you that standard, because I could be asking about standard boiling point, right? Standard, remember, refers to a pressure of 1 bar. So let's say, for instance, I ask you about the normal boiling point. What you would do is you would come over here, right? And you would say, okay, I'm going to find 1 atmosphere on this axis, on my pressure axis. Then I'm going to work my way over. I'm going to remember what these different curves represent, right? This curve here is going to be my melting point curve, right? Because that's where solid and liquid coexist. That's my solid and liquid coexistence curve. Over here, this is where my gas and liquid coexistence curve exists. So I see, okay, yep, this is where these are going to be in equilibrium with each other at that pressure. I come on down here, right? And then this is my normal boiling point, right? So kind of think about why that makes sense. This is where gas and liquid coexist at that 1 atmosphere of pressure, right? You would do the same thing. You get a standard boiling point. You would kind of do this analysis, okay? Now, what about certain situations like CO2, for instance, where we go to try to do the same thing, and we look on this axis, and we say, oh, 1 atmosphere is down here, right? The triple point is actually higher, right? Then, excuse me, the triple point is actually higher when you go through this process of trying to find this coexistence line, all right? So because the triple point's here, this coexistence curve starts here, you never intersect it. So what we'll say about something like CO2, where if we find 1 atmosphere down below the triple point, okay, is that CO2 does not have a normal boiling point, right? What CO2 has is a normal sublimation point, all right? And that's where a solid to gas transition would happen, right? So this temperature right here, we would call the sublimation point, right? The other interesting thing that we can think, so can we make the same sort of declarations about melting points? And the answer is yes. Now, the thing about this melting point line, and I tried to emphasize it when I actually drew this diagram, is that, and it's an important thing to know about this line, and we're going to actually kind of study it mathematically, is that the melting point line here, our solid-liquid coexistence line, it's pretty nearly vertical in a lot of instances. So one thing you might remember from general chemistry is we don't usually say normal melting point or standard melting point. Normally what we say is melting point. So let's say we picked a pressure and we come over here and we did the same thing. Okay, well the melting point would be down here, right? That's the temperature that would correspond to a solid and liquid being in coexistence with each other. Because this line is nearly vertical, let's say I change the pressure to here, and I do the same thing, and what I see is I kind of get the same value no matter what, okay? Now, it's going to be slightly different, but for the purposes of like standard experimental conditions, all right, or normal experimental conditions, or just common experimental conditions, you're going to be looking at pressures where you do this process and you kind of always end up with the same temperature, okay? So this line being nearly vertical is important for us because that's why we say things have a melting point and not a standard melting point or a standard boiling point, right? The other thing I want to talk about is, again, if you have this experimentally set up where you just have one species there and it's a closed system and the only thing inside of it, right, is just that one thing, not air. Like I said, let's use an example of CO2. It's just CO2 in some container, right? You can actually take CO2 gas, remember gas is down here, and you can get it to liquefy, okay, without actually going through a coexistence region, okay? So what a phase diagram tells us is, sure, if I want to take this liquid to a gas to a liquid, one thing I could do is increase the pressure inside my experimental apparatus. You would go through that gas to liquid interface, right, where they coexist with each other. The gas would start to condense. You would see both gas and liquid in your experiment at the same time, right? A really odd thing that happens though is you could design an experiment where you heated the gas, then you applied your pressure change, right? So it went to a gas to a supercritical fluid, right? And then you could cool your gas back down, right? And what'll happen here is you will never see inside your experimental apparatus both a gas and liquid coexisting at the same time. You have your gas starts to pick up liquid properties, right? It's still a gas, but it's a supercritical fluid, okay? Then as you cool it, it just turns into a liquid. So you can actually, in this supercritical region, go through a phase change process that involves a gas to a liquid where you don't go through that condensation process. It's a different process physically because you're kind of following this circuitous route around the critical point that exists here. All right. So that's kind of it for like the basics of phase diagrams. We're going to get into the details of these lines, and we're going to apply mathematics to them. And the reason that this comes after our discussion of Gibbs energy is Gibbs energy is all over this diagram, and we're going to kind of talk about it. Now, why is Gibbs energy all over this diagram? When is Gibbs energy important? When we're talking about isobaric and isothermal processes. So this PT diagram lines up with our understanding of G quite well, and that's what we'll discuss further. Hopefully this was a nice little review. As always, if there are any questions, make sure you get them off to me.